All right, we are starting on Tipler 575, work in PV diagrams. We'll get to the actual PV diagrams here in a second. At the top of 576, he talks about quasi-static processes. Now, when I did the fire piston, and I hit the top of the fire piston, the very top of the gas, some of them were moving up. The piston hit them, sped them up. So really, if you were to look at it an instant after that I hit that piston, the top part was very hot, or had a high internal. Notice I made a mistake there, didn't I? Because hot suggests temperature, not internal. So it had a high internal temperature. And the ones farther away had not changed yet. But then they start to race down, and they're bouncing into each other, and then it mixes. Remember that pressure and temperature are macroscopic properties. They are averages. They are statistical. That's like saying, what is the height of the American population? You do not look at a midget, and you do not look at Shaquille O'Neal, because they are outside the norm. We are talking about average heights. And temperature is a judge of the average kinetic energy of the molecules. So when we talk about temperature and pressure, we are saying after the sample has come to equilibrium. That's what Ryan was asking last time, yes? Now, he talks about then, right here again, notice it says, until equilibrium is restored in the gas, we cannot determine such macroscopic variables as T, P, and U for the entire gas system. Okay? However, if we move the piston very slowly in small steps, so I move it dV, very small delta V, and then we let it come to equilibrium, small delta V, equilibrium, delta V. This is known as a quasi-static process. What does static mean? Not moving, and quasi-static is barely moving. And here's the part that I found amazing, was after, see where it has quasi-static process, the gas is then moving through a series of very small equilibrium states. And then later on we're going to find out that equilibrium states are very important for entropy. Then it says, in practice, it is possible to approximate quasi-static processes fairly well. And right after that I wrote, wow, I was shocked by that. And this is another one of those where he makes a little nugget, and I wish there was like a button I could push it and go, here's what I mean. You know, like every page here I wish I could unpack with the 20 pages of backward knowledge that I can't get out of this. So, blah, 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 blah. Okay, so we already worked out, and I apologize on the homework that I had the units wrong, but okay. Good for you for noticing that, right? So now we get to the PV diagram. Now, over the summer, I gave you a summer assignment which you've probably forgotten about. But let's take just a PV diagram, and if we remember that we have an equation of state, assuming we are not changing the number of moles of the gas. In other words, we're not opening it up or shoving more gas in, right? The gas is fixed. If we know P and V, don't we know T? So let's just draw a very simple PV diagram. You don't have to write this down, just looking at it. And let's just pick some points here. If we look at point A and point B, those of you that have been in AP2 do not get to speak right now. If we look at A and B, which one's at the higher temperature? And the answer is B. Let's think about this as 1 and 2. I am completely making these up. It's irrelevant what the actual numbers are. Well, if we pretend that there's 1 mole of gas, then if P and V both equal 1, then T would equal 8.31, wouldn't it? But let's just get rid of R. Let's pretend that we made up our own unit and it has a unit of 1. Well, right here, P times V is 1. Well, now P times V is 2. Therefore, point A has a greater temperature than point 1 because P times V is a greater number. However, B would be at the greatest temperature because 2 times 2. And obviously, C would be at the same temperature as 1. Do we all agree with that? 2 times 1, 1 times 2. They have the same temperature. Therefore, they would be on what we call an isotherm. Iso meaning same, thermal meaning same temperature. And you hopefully on that homework, you did something where you took P times V, or T, and you kept getting the same number. And if you get the same number, you get these shapes. I should have hit that, sorry. You notice it, it's fine. Something like this. Those would be isotherms, where the temperature, where the P times V would be the same at all points. And as you move to higher isotherms, you go to higher temperature and higher internal energy. All right? Now, the next thing I'd like to talk about, if we get used to seeing that W equals P delta V, we can change that to W equals the integral of that. And as you should know from calculus, integration means area under the curve. So if you have a greater area, more work is done. Well, we can say that mathematically, but I would like you to convince you of that on a PV diagram. So on the top of page 577, he shows 3 ways of getting from P1V1 to P2V2. He goes, and it's almost like what we have here. So he's basically going from point A to point C this direction, or point A to point C this direction. Let me remove some of these isotherms. He actually then does go straight from A to C on an isotherm, which is fine. Okay, good enough, we can see that. So the question is, how much work is done in each of those cases? Now again, we can calculate it. You see how here there's no volume change? That would be an isovolumetric motion. Another word for isovolumetric is isochoric. You may run into that in college. Choric is a Greek word for space. Isochoric, same space. Don't memorize that yet. We're going to do the Murray thing here. I'll keep using it. And after a while, every time I say isovolumetric, I'll say isochoric. Then pretty soon I'll say isochoric, isovolumetric, and then I won't need to say isovolumetric anymore. Okay? So these right here would be isovolumetric, isochoric. But these would be same pressure, which is isobaric, just like barometric pressure, right? So isobaric means same pressure. Isovolumetric, isochoric, same volume. Isothermal, same temperature. And then you remember from the song, adiabatic. Adiabatic means no heat is lost, which means all energy comes from work, because we had our equation. Now, let's remind ourselves. Can you see that, yes?
Yeah.
Why is it that that's a negative? If we compress a gas, we are compressing a gas, yes? Will the temperature, let's imagine it's perfectly insulated, yes? So Q equals 0. If we compress a gas, will its temperature go up or down? Remember the heat piston? Temperature goes up. So we know that if delta V goes down, delta U goes up. Do we agree with that? Yes? We know that for a fact. Well, if, where's my eraser? Great.
What?
Oh, it's right there on the sink.
You got it, okay.
My bad, Murray.
Okay,
That's
so
your fault.
if W equals P delta V, and this is by the gas, yes? If delta V goes down, then W goes down. It's negative, right? Well, I guess the best way to put it is to be negative. Do we agree with that?
Wouldn't delta V be negative too
Yeah, in other words, delta V would be as V goes
Wait.
then? Yeah, because
No.
that.
yeah,
That.
there we go.
As V goes down, W would be negative, yes?
Yes.
Yeah. Wait.
Okay, so I should put this right there. Yes, we agree with that? Now we've got it, okay?
Yeah.
So, as V goes down, it compresses. W is negative, yes or no? Negative change of volume, negative work done by the gas. The gas is not pushing up, it's not doing work, it's doing negative work. Okay? Then W would be negative. and a negative times a negative is a positive, and it gains temperature. Let me do it again. The gas is compressed. The volume change is negative. By this equation, if delta V is negative, the work done by the gas is negative. What about pressure? When is pressure negative? Never. That makes no sense, right? Because that would mean a negative number of molecules hitting the wall, I guess. Yeah, even going one step into that little void makes no sense. Yeah. All right, so once again, volume goes down. This is, volume's down. This is negative, and a negative times a negative gives me a positive. That's why that equation makes sense. Now you could also write it the other way, which is that would be the work done on the gas by the piston. Okay? So if we look here, if we have isovolumetric processes, ladies, if we have isovolumetric processes, the work done is 0. So that means to go from A to D and no work is done, and to lower the temperature, what must happen from A to D? This equals?
0.
Let's do this. A to D. We understand what we have here. Process AD.
Yep.
W equals
0.
0, since delta V equals 0, yes?
Yep.
Then delta U equals Q. Is this an increase or decrease? Oh, sorry. What's our delta T? Up or down? Down.
Negative.
Therefore, delta U equals down, and Q is negative. That's an endothermal, that's an exothermal process. You have to extract heat from the gas. Once again, moving from A to D, since P times V is a smaller number, we know that delta U is going down, which means that the temperature is going down. Since it's an isochoric or isovolumetric process, we know that W equals 0. From the first law of thermodynamics, we know that Q equals delta U. And if this goes down, then this must be negative. This would be heat removed from the system. How do you take heat out of the system? Let's make it simple. Ice. Now, does it have to be ice? No, it could be colder than that. You know, liquid nitrogen, liquid helium, yeah, whatever it is. And once you get below liquid helium, it would be lasers that literally touch the molecules and slow them down. Yeah, that's wild that they actually pulled that off. All right, over here, what happens from B to C? Let's talk through it. B to C is what kind of process? Isovolumetric. Therefore, W equals 0. Then, delta U equals?
Q.
Delta U equals Q equals positive or negative? So, Q comes out as well. So from A to D and B to C, they are losing heat. We good on that so far?
Is that why whenever we did the vacuum thing over there, is that why it got
Because,
colder? Because we're losing pressure.
Since there's no work.
Yeah, yeah. And if you think about it for a gas, or sorry, for a liquid is basically isovolumetric. Remember, it's incompressible, basically. And so, but you by losing, well, no. The gas above it by reducing the, no, I don't want to go there. I think it could be as you're pulling the gas out of the bell jar, it is decreasing its temperature there too, but the biggest decrease in temperature of the water was because it was evaporating. And remember that evaporation is a cooling process, because remember the billiard balls, and as they were bouncing out, the ones that were left have less energy.
Yeah.
You almost got me trapped there.
Sorry.
Appreciate that. So now in this case, from A to B, the volume is,
Increasing.
so let's do this. process AB. Delta V equals
Positive.
positive. Do we agree with that?
Yeah,
Yeah.
go ahead.
We have a positive change of volume, but the pressure stays constant. We have to talk about that in a minute. That's going to be wild. Okay? Positive change of volume. So W equals
Positive.
a positive. Do we agree that from A to B there's positive work done?
Yes.
But we also, from A to B, would we agree that TB versus TA is, which one is greater, B or A?
B.
B, because
Oh, wait.
PV is bigger than PV. Do you already see what we're having here? So that means if TB is greater than TA, then delta U equals a positive.
Yeah.
Yes? So now I'm going to write the first law of thermodynamics here. Screw this. That's hacking me off. Let's start thinking more advanced. I'm just saying that's what we're going to use most of the time. So let's just use the right equation. What is this? That's a positive. Do we agree with that? That we agree that in the final analysis that must be positive. Because we look at it, the temperature's gone up. Has to have gone up. This is
Positive.
positive. So that's a negative times a positive, which is actually a
Negative.
negative.
U has to be positive.
So if this is a negative, why is it a negative? Remember, if you compress a gas and its temperature goes up, then when you expand a gas, its temperature goes down. So as it's expanding, its temperature wants to go down, but its final temperature actually went up, which means that dq is a positive, and we can say that we can say that, let's look at our equation. This is how you should solve these problems. We know that to be positive. Why?
Temperature goes up.
Temperature goes up. We go to a higher isotherm. Remember the isotherms we drew? So the isotherms are increasing. This has to be a positive. This is a positive or negative?
Positive.
Positive, and a negative times a positive is a
Negative.
negative. So this one must be more positive to make up for it. So which of those three is the biggest number?
Q.
Q is the biggest. Now look down here. Don't we also go here and we increase temperature? Isn't there positive work done here? Which would try to cool it down, or sorry, would reduce its internal energy, so you must be adding Q to make up for it. So in both of these cases, an expanding gas that increases its temperature must absorb heat in an amount greater than its expansion decreases its temperature. Now let's look at this one. Yeah, you didn't see me there. I was kind of, it's fine.
No, I did see it.
Yeah, was that kind of weird?
No, like you were close, so I wanted to turn the camera on. Zoom.
Now let's look at a weird one here.
Oh.
What about A to C?
Oh, no.
Everybody, we're going process AC. By the way, as we're doing our PV diagrams, which we're gonna have to spend some time on PV diagrams. Look here, look where I put the arrows. I did not put them at the end, did I? At the end, they could clash and it would be hard for you to read them. Put them in the middle of the line so you know exactly where it's going. Clarity of writing is clarity of thought. Here, we are doing process AC, which is what kind of process?
Isothermal.
Isothermal. If that's true, Most of the time. No. That's not going on YouTube. Yeah. Okay.
Demonetized.
So what is this?
Demonetized.
Yeah. What is this?
Zero. Yeah.
Zero. Isothermal means same final internal energy, right? So now, is this increase its volume or decrease its volume? Well, actually, once we get this, let's just follow the white rabbit fast. And so we get dW equals dQ. This is a positive value because it increases its volume. And how much energy, how much heat does it gain? The same amount of work that was done. Isothermal, T and U both stay the same. Then Q and W both must move, but in equal and opposite ways.
Ooh, the song didn't lie.
Starting to make some sense now, isn't it?
The song doesn't lie, you're right.
Okay. How are we feeling about that? Pretty good?
Yeah.
Now, next thing I want to talk about. I want us to look at this. I bet you didn't think this little diagram was going to take us that long. But this is actually helping us for the next chapter, so I'm willing to spend the time on this. Now, what about the difference between, I want to talk about these things. I want to talk about ABC, and I want to talk about ADC. In other words, we're going from A to C, please stay over here. We're going to go from A to C by two different means. So, first of all, if we do A to D, W equals A to D, W equals 0. And here, B to C, W equals
Zero.
0. Do we all agree with that?
Yeah.
Isovolumetric. From A to D, no change of volume, no work done. B to C, no change of volume, no work is done. Are you good on that so far?
Yeah,
Okay.
You just switch the AD.
Well, no, because this is BC. I'm only talking because we're going to go this way, but I'm saying in this segment, you see how there's no work done.
Yes.
Here, the first segment, no work is done. And here, the second segment, no work is done. All right, so let's talk about, yeah, oh no, I skipped it. That's supposed to be AD, right? Sorry. Oh, I totally screwed them up, didn't I? Wah, wah, wah. Wah, wah. Yeah. Okay, so now look at, what about AB? We need to talk about AB, and we need to talk about DC, don't we? Would you agree work is done in both of those cases, yes?
Yes.
Let's first do it mathematically. Or, yeah. In this case, we have W equals P delta V. What's my pressure here?
Higher than.
This is AB, this is 2, and our difference is 1. And here, we have 1 times 1. Again, I'm using stupid numbers, but the concepts are still valid. So notice here, more work is done on the higher isobar than is done on the lower isobar. We see that mathematically. We can also see that this area is smaller than this area. And the area of the curve, the area under the curve tells us the work done. Yes? I would like to talk about this conceptually now, and this is going to be one of the harder things that we do. At least it is for me. For you, if it's not, but good for you. I want to talk about how we would actually do these processes. Oh, and likewise, if we did the A to C, you see how if we go ADC, that would be the smallest amount of work. From A straight to C on the isotherm would be more work. Then going from ABC would be the most work that would be done by the gas. Do we see it?
Mm-hmm.
That's just graphically. How would we do an isovolumetric process, and how would we do an isobaric and an isothermal process? So, for an isovolumetric process, that's easy. You have a container, you put the object in it, you seal off the container, you add heat or you remove heat. Couldn't be simpler, isovolumetric, right? Now, in that case, let's imagine we have an isovolume, we have a jar, we we take an object, we put, again, obviously this is liquid, but let's imagine we take something, we filled it with gas, right? And if we started to put heat into it, let's think on the atomic level. If we put heat into the molecules, they begin to move faster, and faster moving molecules bouncing off the side would create more pressure. That's pretty easy. In that case, with PivNerd, if this is a constant, more temperature gives us more pressure. So simple, we're all done with that, right? But what about an isobaric process? The pressure on it is the same. I know you did this with Marek probably last year, and you probably spent some time on it. So do you remember what it was?
At least from what I remember is you put it in a piston and you put the fire in the piston and then just let it go.
Let's say we have our piston here. Well, I mean, I got that crazy all of a sudden. Crazy, Murray. Don't know what you're talking about. Anyway, so if we have this piston here and we have the gas molecules here, let's imagine that I put a mass on it. And let's say the piston itself has mass. We'll say that this is m. What the heck? We'll just make them all equal to m. So we have a mass of 2m and a force of 2 mg and an area of A. Couldn't we find the pressure? Then if we add heat to the gas would want to expand, wouldn't it? But you see how the force on it is still 2 mg. So therefore, as you add heat, it would just expand. Its pressure would not increase because it's still pushing on the same amount of mass. Now again, as it pushes up, yes, its volume increases, but its pressure stays the same. But if P is constant and V increases, T increases. Let's talk about that. You've let this expand. You have the same number of molecules in the cylinder. In order for the same molecules to create more volume, don't they have to move farther in the same amount of time? Which means they have more kinetic energy, they have a greater velocity, which is a greater kinetic energy, which is a greater temperature. And if I wanted more pressure, I put more mass on the cylinder. Now we have a greater pressure. If I didn't change the temperature, if this is a perfectly insulated container, and I add more weight, now I have 3 mg over area. Gentlemen, are you with me so far? I have 3 mg over the same area, so I have a greater pressure. But I have not changed the temperature. That means the volume must go down, because you're going to push on it harder, which will compress it. But if it was isothermal, then we'd have to get into some other issues. Okay? Go ahead.
I don't know.
Gentlemen, listen to the
You've
question.
been counting the mass of the piston?
As M.
Oh, like the, okay, never mind.
Yeah, so I'm just trying to make this easy. I just went M, M, M.
I was like,
We could, you know, we could do the thing which you see on AP tests where they say they have a frictionless. Again, try to imagine having a frictionless cylinder. I dare you on that. And then they also say a massless piston.
Yeah.
Again, how the hell you would do that?
What's your
Okay. So are we all following how to do a constant volume, or sorry, constant, an isobaric process, the same weight on it? Now I've never tried this. And this is like, if this works really good, I still don't want to know if I want to put this like, maybe like, you see this guy on YouTube? Yeah. Yeah, what the hell? Yeah.
That was pretty epic.
This might be a complete disaster. I have no idea. I'm going to try though.
Alright, I'm getting at the chip score.
Yeah, this is when Murray. This is when everybody gets excited. Murray's going to try something never tried before. Do we all remember? We had our molecular model of a gas, yes?
I'm too sure it's on.
Why is Olivia always at 2
Rachel has 3.
I can't say I do, so yeah.
Alright, I brought the popcorn.
I think we've already gotten through a lot today, haven't we? We've gotten through a lot already.
I mean, my finger always.
I've kind of gotten to the next chapter. Did you do AP2? So all this is, well, he covered this, right? To this detail or more? Just from our first PV diagram.
Eric, you have to complete it.
That color looks good on you.
Oh, you know what you show Rachel?
That scrunchie looks good.
You know what you show Rachel? A cartoon we watched.
No, we're not.
It's not a cartoon, the ad.
Yeah, how cool would it be if Tipper was still alive and we could like Skype with
She'll get a
him?
call.
Yeah. And even actually Randall Knight, there are things in his book I would love to ask him questions. I've got stuff I'm like, I don't follow.
Let me see it, and I will share the pain with you.
No.
All right, so here's our device, and again, this may be a complete disaster.
About 85 years old. That's like so was like, she's about 60. Old, you know?
It was honestly a little.
Actually, I just changed those from the red down to the bottom for any of my, whatever, the OCD people or whatever that just couldn't handle red in the opposite one. Okay, so, I don't know if this is gonna work, but we're gonna try it. Where's the, there it is.
Nice.
You see how they're all randomized now, right? And you can see so if I up the volume, up the voltage is like a greater temperature. Less temperature. And you see how more temperature causes the pressure to go up. Right now it's at constant pressure, isn't it? Well, the temperature is constant and the pressure is constant. But if I were to decrease the pressure by lifting it up, or increase the volume, okay, now to increase the pressure, I don't know if this will work, never tried it. Did it go down a little bit, or is it not at all?
Yeah,
Oh, they're all together now.
Now they're all together, yeah.
Eric, how is yours now?
There we go. So let's try this again. Here we go. Let me try these. I took little masses to put on them. But you saw how it compressed it down, yes? Okay, and that may not have been that great, but you see the idea about me adding more force here causes a greater pressure for the same temperature. Same temperature, greater force, less volume. Okay? Does that get the idea a little bit? I'm just, yeah, meh. I'll put that away later. Yeah. All right. Next things. Now that we've talked about the PV diagrams, I'm not sure, just, ladies, just very quickly, without going into too much detail, you can see there at the bottom of the page, they have a different conversion factor. In other words, if instead of working in meters cubed and newtons per meter squared, are we going?
Yeah.
Okay. Instead of going in meters, instead of pascals and meters cubed, we could be in liters and atmospheres. So if you'll notice here in the middle of 576, it says that 1 liter atmosphere equals 101.3 joules. So you can actually, if you're working in one, do your calculation, and then do your quick conversion. Is that something we should spend a lot of time on? No, it's just something you should keep in your back pocket when you see that later on, okay? Now, here we go with our very first, our very basic calculus example of an isothermal process. If we know that isothermal, then what's constant? The temperature is constant. Delta U equals 0. Okay? Well, we have W. Actually, I'm going to do it this way. dW equals P delta V. Yes? Are we okay?
Why are you so bad at like?
Okay. Well, does it not, please gentlemen, try to stay with us here. I know this much work in one day and advanced physics is hard. So right
You got
here,
roasted.
yeah, that was a roast, and I hope it was a good roast. Here, do you agree that P and delta V that P is also dependent on V? Okay, so we have to put in our equation of state. This is our equation of state. We solve for P, and we plug it in. So now we have dW equals nRT over V times dV. But we don't want a little bit of work, we want all the work done, don't we? So we put our integral signs on, and this just becomes W. We take out the constants, which are nR and T, because we are talking about an isothermal process. And that gives us a very simple integral, which we keep seeing, don't we? Over and over and over. We've already seen it several times, and we've just started this year. However, I need to add something for those of you that are in Calc 1, and I apologize. Cleve is going to get to this in a bit. When we do a delta V, a dV, and we take the integral of it, we actually get delta V. If you add up all the little dVs, so let's do this. If I had this, when I add that together, I get delta V. Do you agree with that?
Yeah.
But if we don't start at 0, we have to know, this basically says our initial and our final minus initial, which would be our final minus our initial. So we now have nRT equals the natural log of V evaluated from V1 to V2, which gives us nRT, the log of volume 2 minus the log of volume 1, and from our logarithm rules we know that that's division, which gives us nRT, the log of V2 over V1, and that's how you calculate the work done in an isothermal process.
Pretty epic.
Simple enough, huh?
Yeah.
Okay, moving on. By the way, at the end of the chapter, he does another gigantic one of an adiabatic process where where Q equals 0, and it's a pretty big thing. And because we're behind this year, I'm going to say if you would like to go through, it's a lot of logarithm rules and stuff like that. So we're not going to waste our time. We're just going to jump to the conclusion. Is it horribly difficult? Yes, no. If you're good with logs, you can figure it out, but it's not easy. Okay? Now, time for us. Are we good here?
Yep.
And that's in the book. I mean, that's a straightforward. John Michael will see that and go, yeah. It's about one of the simplest derivations of the year. So now, I would like to talk about heat capacities.
The one I understand.
Yep.
Let's talk about heat capacities. On page 578 at the bottom of the page, he talks about heat capacities of gases. And he says, if we were to add heat, Q equals M, no, not M.
No.
Let's look at these two equations. I'm trying to make those obviously big C's and not little C's. Yeah, that's as big as I'm going to make them without wasting a lot of ink. If we were to add heat at constant volume, boom, we have constant volume. You start to add heat, the pressure will increase, but its volume will not increase, right? But what if you add it at constant pressure? At constant pressure, doesn't the volume increase when you add heat? You have a cylinder. Remember, you have the piston with the masses on it. You start to add heat. The molecules will start to increase their motion, and it will push the piston up. But if the piston moves up, its temperature wants to go.
Temperature wants to go down.
Remember that an expanding gas's temperature goes down. So if you're at constant pressure, remember we had the constant pressure, the isobar? And remember that work was being done, so its temperature wants to go down, but its final temperature actually went up. So we actually have to add more heat. In a constant pressure change of temperature, we have to add more heat than in a constant volume change of temperature. And we can actually show that. I'm stupid that I didn't think of this before. If this is P and V, let's do our simple little PV diagram with 1 and 2, right? Well, if we start here and we go to here again. Oh, and here. That was making this. That's on the fly, as you can tell. So if we go from C to B, no, almost got it, almost got it. Yeah. You see how these two are at the same temperature because they're on an isobar, or an isotherm? And we go to that point, which is obviously itself at the same temperature with itself because it's in thermal equilibrium. Anyway, right here, its volume is not changing. So W equals 0, and all we have to do is add heat at constant volume. But now, we're going to go from A to B isobarically at constant pressure. And in this case, it's expanding also. So as it expands, its temperature goes down. So to reach the same temperature, we have to add extra heat. Think about the gas expanding as someone sucking heat off of it, right? That'd be the equivalent of you just walking up and putting an ice pack around it. Here, it's not expanding, it's not losing heat, right? Due to the expansion. You put Q in, temperature goes up. Here, as you add heat, it expands. Crap, it's cooling down. I gotta add more heat. It expands more. I have to add more heat. So, this Q is greater than that Q for the same delta T. So, let's learn some cool things here on the next page. We're on 579. So he talks about when heat is added to a gas at constant volume. Now, that's why he's talking about a gas, because we're generally in thermodynamics, right? Which is mostly talking about gases. But also, do liquids and solids, do they change their volume much? They do change. Remember we talked about linear expansion? Yes, remember the expansion gap and so forth? But is it a large amount compared to a gas? It's enough that we can neglect it. It's negligible. So we end up with this equation. Yes? Okay, same one that we had, but we made differentials out of it. This is equation 1918. That may seem, oh, sorry, that was stupid. I blew that. Sorry. Yeah, so we get here. What did I miss? No, I'm sorry. That was really stupid. My apologies. Okay, so since CV, which says constant volume, then delta V equals 0, then W equals 0, then du equals dq equals this. Do we agree with that? So now, CV equals du over dt. which is equation 1918. Now, here's what he says. He says the heat capacity at constant volume is the rate of change of the internal energy with temperature. Like a slope, the rate of change of the internal energy with temperature. Since U and T are state variables, they define the state, not the process. In other words, it doesn't matter how you get there. This equation holds for any process. You guys may not understand what I just said. That's deep, man. That was, so let me show you why that was deep. Now, would you agree that this is isobaric? And this is isochoric, yes? Which means isovolumetric, yes? You remember our isotherms? We have one isotherm that passes through here. We have another one that passes through here, yes? Such that TB is greater than TA. Are we in agreement with that? Yes? Okay? Yes, we're all good with that. TB is greater than T8 or TC. If I am not asking about the work done, if I don't care about how much Q there is. Now, if I wanted to go from A to B, just A to B, and I'm like, how much potential, how much energy is there? Or, I'm trying to find the delta U, Q, W, etc., right? Say, well, I can find W, I've got P, I've got delta V, I've got W. Yeah. If I knew those two temperatures, I could find the delta U, couldn't I? But I could also use this equation. Is it at constant volume from A to B? No, it's at constant pressure. But aren't the temperature from A to B the same as the temperature from C to B? And those are state variables. If there's a different amount of Q from A to B than there is from C to B. Some of you need to pay attention. I know you're struggling. You're not used to this. If this is more Q, remember at constant pressure is a bigger Q than it is here. But the delta U is the same. Because delta U is only dependent on temperature. So it doesn't matter how I get from this isotherm to that isotherm. Same change of temperature, same change of internal energy. And this equation will work for all processes. And so now I've got du. I've got du, because for this gas, I know CV. So then I find the work done, now I know Q. And here, there's no work done, I already found Q, constant volume. And any other process that I can come up with, and pretty soon we're gonna do adiabatic processes, it will work as well. To find delta U, not to find W, but to find delta U. Okay, now, if this is true, what about at constant pressure? Because we said that CP was bigger than CV, didn't we? Well, let's prove that. So if we start with QP equals CP delta T. And then we put that in, and we take the first law of thermodynamics. Well, he does it this way. QP equals U plus W, right? Because we move the W to the other side, it makes it positive, right? And then he goes, let's put it all in, equals U plus P delta V. And then does he take the differential, is that right? Yeah, then he takes the differential, and this would be CP delta T equals du plus B delta V. these are both dependent on V, aren't they? I'm sorry, they're both of them are dependent on T, etc. Okay, so in this case, we now actually have to take this and we have to do the product rule. Okay, and so here, what we do is we put it in, we say P dV. Now, later on when we look at this, we say, but the pressure is constant, just take it out. But we're gonna do this the long way. So, and we have PV equals, yeah, sorry, I'm not the huge product rule person here, but if we take, how do I write this? He does, yeah, okay, sorry, yeah, PV equals nRT. Then using the product rule, it's P dV plus dPV?
Yes.
Is that right?
Mhm.
That's the product rule, okay? And what's that equal to? At constant pressure?
Zero.
That equals 0. So then we just get PdV. Right? So now, once we get to that point, what's that?
Nothing.
Yeah. This equation right here, didn't we just define that? We just said that CV equals du over dt, didn't we? So that du for all processes equals CV dt. Right? Didn't we just prove that? So now down here, we now have Cp dt equals Cv dt, which equals nR dt. And what do we see everywhere? We see the dt's, so they can disappear, and that gives us a glorious result. That Cp equals Cv plus nR, which shows us that Cp is bigger than Cv for any ideal gas by a value of nR. If you look at the first column, remember we just talked about how Cp is bigger than Cv, yes? Well, let's look at the Cv column. And you notice we have 12.5, 12.68, etc. In your anybody got their calculators there real quickly? Oh, you don't want to leave right now, dude. It's about to get good. Sorry. So, if we take CV, you see the second column, if you take the CV prime and divide by R, which is the third column, what is that number 1.5 equal to? What is 1/2 equal to? 1.5 equal to? 3/2. Do we remembered an equation that we had U for an ideal gas equals 3/2 nRT, which also equals, and then that 3/2, remember the end, we had C prime, which was the end. But look down here, now we have diatomic gases. Diatomic gases are not 1. Do you see how all of them are 1.5 roughly? But the diatomic gases are 2.5. 2.5. We need to write this down. We're about to get a big deal, super big. And this is again. I'm going to leave you with this, as they do in a show. Leaving you with this, dun dun dun, and then we'll talk about why, which has taken me 4 years to figure out, and I finally have it. Here we go. For monatomic. Monatomic gases. We get that Cv prime over R equals 1.5 approximately, which equals 3/2. We get that for diatomic. Cv prime over R is approximately equal 2.5, which equals 5/2. Remember this equation? We derived this equation from the kinetic energy of the molecules. And we said, due to the equal partition theorem, which says that a gas statistically will give its energy to all available modes of energy. And we said, if these are monatomic gases, and if we are only talking about their translational energy, meaning straightforward energy, they can move in the x direction, they can move in the y direction, and they can move in the z direction. There are 3 modes of energy storage. And each mode is 1/2 kT or 1/2 nRT, which gives you a monatomic gas of 3/2 nRT. But a diatomic gas has 5/2. It has 2 more modes of energy storage, which is rotation. So if this is the molecule, pay attention, a diatomic gas can rotate this way, and it can rotate this way, which are 2 more modes. However, and this is what we're going to find out next time, 2 things. 1, monatomic gases are running into each other all the time, but they do not rotate. Try doing that with billiard balls. Strike them together, and they never rotate? I don't think so. And here's another amazing thing. There's only 5 modes of storage for a diatomic gas. 1, 2, 3, 4, 5, but not 6. And then, if we get to, where is it? It's not on here. However, we do find out for molecules that are solids, and I can't find that very quickly. For solids actually have this answer. Which is nRT, sorry. 6/2. What the hey? We have a molecule here. It can move this way, and this way. That's its kinetic energy. Anything that's a squared quantity in the energy or momentum is a mode of storage. 1/2 mv squared, mode of storage. 1, 2, 3. 1/2 I omega squared. 1/2 kx squared. If ever we'll turn very quickly, and we'll end with this today. Look at page 583. And he has a picture of molecules in a crystal lattice. So let's just take these 2 molecules here, and let's imagine they're attached by springs. And instead of springs, what's really happening there?
They're molecules.
Those are the intermolecular forces. That's supposed to be the 3rd dimension, right? So each one of those molecules can move this direction, x, y, and z, or I, j, k hat, and I, j, and k hat, right? All 3 directions. But because there are intermolecular spring-like forces in between them, that's 3 more modes of storage for energy, and you get 3 nRT. 6/2, 1/2 for each mode. And these are some of the first things that led us to the internal structure of the atom. These simple numbers of calculating and finding out that almost all monatomic gases have basically 3/2 nRT for their energy. But diatomic gases are 5/2 nRT because they rotate, but not along their axis. And we'll talk about that next time. Dun, dun, dun. And you're lucky that this year I finally understand why.